Together, right?
Yeah.
Sweet.
Okay, this on? Great. Yes, so this is starting the session of what FRB people can learn from other communities, hopefully, or maybe at least learn what not to do from other communities as you start to move into this population scale. So I'm going to be talking about supernova, and just to provide a little bit of context here, this is what the supernova field has looked like for the last few decades. We've gone from the fact of, in the early 1990s, discovering a few dozen supernova every year, to now our wide field optical surveys, which image almost the entire sky every night. We're finding over 20,000 supernova and other explosive transients every single year. This has opened up a wide variety of things for us, things like identification of large samples of supernovae, discovery of intrinsically rare subclasses of supernovae, and just new regimes of how to study objects that we knew about before, but just have new types of data we didn't. And in particular, what the organizers asked me to talk about in this talk was focusing in a little bit on the host galaxy follow-up, and in particular, discussing the implications of this and just how large our samples are now for the scale of host galaxy follow-up for supernovae, how the follow-up is typically done, and what we can learn from it, and then what, in our opinion, the community could have done differently if we were starting fresh. So I'm going to try and hit on each of those in the next few minutes. So just as a bit of a starting point for you, clarification caveats, I'm going to focus on cases where the host galaxy is unambiguous. In supernova optical surveys, we typically ground-based something like arc-second, sub-arc-second localization. So usually there is no question for most of these about what the galaxy is. That's not always the case, but that's what I'm going to focus on now. I'm also going to focus on optical host galaxy follow-up, mostly just for time constraints. There's a lot of interesting things you can do at other wavelengths in radio and X-ray as well, but I'll focus on optical. And then my examples are going to be slightly biased towards core collapse supernova, just because that's what I study more so than some other examples. Okay, so other people have already talked about this, but in general, when we're studying supernovae, what we can try and actually learn. How can the host galaxies or environments help us? There are two big things that tend to come up, at least for core collapse supernovae and other things as well. They can really help you constrain the age of, well, in general, you're trying to learn about things of the progenitor scenarios and disentangle those for different types of supernovae and other peculiar transients. And the host galaxies can really help you constrain the age or the delay time for a given type of explosion in cases where it's far enough away, you're never going to detect the actual progenitor itself. And then also you can constrain other physical conditions that may be required, things like metallicity, or maybe local stellar density if you need a stellar cluster, or other things like that you can get through environmental studies. Okay, but so again, plan for the next 9 minutes or so, the rest of my talk, try to give you a few examples of data that have been useful in supernova host studies to tackle each of those questions, how we've typically used them, our typical sample sizes, and the current scale and method of supernova host follow-up, and then try to conclude on a few lessons learned or words of caution about how to actually build your samples, which is, I think, the biggest caveat or thing we've learned about supernova studies for the past few years. Okay, so types of data that have been useful. One of the big things that we can do, I have just a few examples, are using just bulk galaxy properties as a proxy for the age of your type of explosion. This can be useful if you think about it, if you're trying to tell the difference between something that might be the explosion of a massive star, maximum life until it happens of a few million years, or something that comes from a compact object merger that has a delay time until it will eventually merge, and that can be a gigayears or so. Bulk galaxy properties can help with this. So this can be really basic, like early on it was discovered quite early that, what we now know are core collapse supernova only explode in star-forming galaxies, whereas what we now know are thermonuclear type 1a supernovae explode in a wide variety of hosts, including ellipticals that only have whole populations that clearly come from very different ages. But in general, we can also do much more detailed studies by using these bulk galaxy properties as a proxy for age. This can happen if you look at, for example, delay time distributions of different types of transients, or trying to examine their rate as a function of the stellar population age. So what I'm showing you in the bottom here is an example of a delay time distribution for type 1a supernovae, so things that come from the explosion of white dwarfs. So like what is the rate of each of these as a function of age? And this type of study is incredibly useful at constraining different progenitor populations. And this study I'm showing you here, it was actually done with a sample of only about 132 type 1a supernova. The caveat I'll give to that, it was 132 supernova that exploded in a set of about 66,000 galaxies that were very well understood in terms of those 66,000 all had detailed spectra that allowed you to map out their detailed star formation history from doing stellar population synthesis and modeling those galaxies. And in addition to that, those 66,000 galaxies, it had a very well understood detection efficiency for the supernova within those fields. And it was by coupling those together, you can come up with this delay time. Because if you think of it, if you have a set of galaxies, you have a well understood star formation history, and let's say you know the delay time distribution, then you can easily calculate how many supernovas should explode in each of these as a function of time. So you can invert that. It becomes a linear algebra problem to sort of, if you know how many supernovae you were and you think you well understand those biases, you can flip that around to get a delay time distribution. So this is very powerful, but you need to have a very well understood population that you did for this. And even within that, what I would say is this is useful for certain types of explosions. For type 1a supernova, which have delay times between, 0.1 up to 10 gigayears, this works well. But if you look at the low, this is just 3 bins in time, which is useful for understanding explosions of white dwarfs. But the lowest time bin here goes all the way up to 500 megayears, which is about a factor of 10 higher than the last massive star that's going to explode. So if you want to learn about details of massive stars exploding, you need much finer time resolution than what you're getting from this. So you are going to need either much bigger samples that, again, are still very well understood in terms of detection efficiency, or you need different methods. So in practice, how we've been doing this in the supernova field, when we're trying to understand in more detail different types of core collapse supernovae that come from massive stars, which all of which look like they just have really small ages in those other types of samples, is to look at more the local environments. And often this has been done for very nearby events where you can take images like the one I'm showing you here, and often not just general galaxy light, but looking at H-alpha images or rest frame UV images as proxies for either the ongoing or quite recent star formation. And then typically you could look at the explosion sites of your galaxies relative to this. So you can see small circles in those top two where different types of transients exploded. And often how we've done this is, at least the initial swath of studies like this, was just looking and trying to understand what is the correlation when you have a large sample of a certain type of explosion to, let's say, the H-alpha emission in your host. And then you can build plots like the one at the bottom, which is just showing you, not actually, oh, I do have a pointer. No, maybe I don't. Okay. This is just showing you sort of fraction of your total sample of supernovae. And then on the x-axis is where it falls within the cumulative sort of H-alpha star formation in the galaxy. So what fraction of the pixels in that image are brighter or fainter than what you see? So if you directly trace your star formation, it's going to be a 1-to-1 line, like that dashed line there. Whereas all those things showing up in the upper left of that plot are things that actually tend not to trace the H-alpha or star formation in their host galaxy quite as much. So a couple of things that have fallen out of this type of study are things like hydrogen-4 core collapse supernovae more closely trace H-alpha in their hosts than hydrogen-rich ones do, which is generally interpreted of those are younger populations, the H-alpha is still there, and so likely higher mass stars. And similarly, we get some unexpected results, like a class of supernova that seem to be crashing into large amounts of material in their circumstellar environment, actually don't trace the H-alpha in their host galaxies, which was unexpected because people thought they might be examples of luminous blue variables, which should be really high mass stars. This is showing that that's not what type of progenitor is likely actually exploding in these cases. You almost certainly need something that is older than what stellar models think for that type. So this is the type of thing you can get for examples where you have sort of large samples that are close enough to do this type of thing. And now recently, this type of study has been shifting to using integral field units to actually not just do H-alpha maps of the regions, but actually do get spectra of each of these pixels and do things like mapping out the star formation history locally at the site of the supernova, which is more powerful than the star formation history of the galaxy as a whole, where you start to need really large samples to pull out meaningful information. Okay, and the last quick example that I'm going to give is metallicity, which trying to use as a probe, again, of different extra conditions that are needed for different types of stellar explosions. So this typically comes from spectroscopic measurements and getting the gas phase metallicity of your host galaxies, not always, but a lot of the time. And sometimes what we found in supernovae is large global preferences for certain types of transients. I think everyone in the FRB community is familiar now with the idea that superluminous supernovae and long duration gamma ray bursts seem to explode preferentially in low metallicity tiny dwarf galaxies. This was very clearly present in all of the data early on for these. But we can also, with the large populations we're getting for supernova, if you again have well-measured samples, you can start to, in well-controlled samples, you can do more detailed questions about how explosion properties themselves can correlate with metallicity as well. So what I'm showing you here in this plot is a study that looked at how the rate of hydrogen-rich versus hydrogen-poor supernova change as a function of metallicity on the x-axis. Okay, and I'm going to speed up quickly here. And the main point here is you see a correlation between those two. But again, this is done with only 100 supernovae or so, but it had to be one where it was a volume limited sample and you had very well understood biases to pull this information out. So an important note in terms of the scale of the follow-up we've been doing, you saw that some of the examples I gave you there only had 100 objects or so, but often it was from things that were very well understood samples to begin with. And the biggest thing I'll say about scale here is that while the number of supernova discovered per year is high, the number density of useful events is still kind of low to make sole or primary use of existing spectra, like multi-object spectrographs. And so there's a couple effects of this. One is that it's actually quite common still for a lot of supernova host studies to just use photometric data only, like the type I'm showing you here, where you use SED galaxy modeling. These are a couple recent examples, including one with like 1,000 host things. Important caveats here are what useful information can you get. In particular, you can get masses, but it's hard to get things like metallicity out of this, although people certainly still do try. I can talk more about that later. But the other effect then of just how we do spectroscopic follow-up, usually this is still limited to us for either tailored samples of objects of interest that are typically only dozens of objects that people get one-off one at a time, like superluminous supernovae, GRBs. This can be, 20 to 60 objects usually make up a paper there, or trying to use archival or coordination with some of these large scale structures like SDSS and DESI, but you really want to make friends with those people. They often have spare fibers, but you usually are not going to make use of all 400 of them yourself for transient follow-up. And then IFU studies. Okay, so just to wrap this really quickly into the cautionary tales and lessons learned, the biggest thing I'll say here is that host studies work well out of the box when you have progenitor scenarios that are very different. For instance, long and short GRBs, which we know now it's like young massive stars exploding in bright star-forming regions and compact object mergers offset from their galaxies. Those are very different. Once you recognize that there are two classes of GRBs, these host populations separate out very well out of the box, but almost always, otherwise you have to be incredibly careful. Subtle effects can be uncovered, but only when you really understand biases in your sample. This is something we knew about in supernova studies, but I would still say there are a lot of disagreements and papers with conflicting results in the literature, mostly because of different biases that were present. Just as a snapshot of this, there was a lot of early debate on how metallicities of hydrogen-poor supernovae, whether they actually were higher or lower than other events. This was sparked by interest in long-duration gamma ray bursts and the idea that some of these are associated with them. There was a lot of conflicting results. A big part of this turned into the fact that early supernova studies were actually targeting individual galaxies, which it turned out were biased with higher metallicities. That affected a lot of these early results. And then similarly, things with various rates, you have issues with targeted versus untargeted surveys and magnitude versus volume limited samples, which have led to a lot of disagreement in the literature that now it's taken a while to unsort. And so I'll just finish by saying that I really do think it's an important point for the FRB community. We talked about oddballs versus unbiased samples earlier. You can do both, but I think it's super important to think about ahead of time. There is a whole generation of wide field optical surveys that found thousands of supernovae that I am of the opinion, others might disagree, that we're probably never going to use them for rates because we basically have no idea anymore what the selection function was for follow-up for those. And so it's just too hard to disentangle now after the fact. And in fact, for supernovae, a volume limited sample of supernova from an untargeted survey was only just published like 2 years ago for the first time. We're still building that sample now. So FRBs have a couple advantages over supernova. Most of your surveys are untargeted already. They're blind on the sky. That's great. You also don't need to get spectroscopic follow-up to classify them like supernova do. But on the other hand, the fact we have different spectroscopic classifications of supernovae is part of the reason we've been able to disentangle all these interesting trends. If you just put every supernova on some of these plots, it would just be a mess. It would be quite hard to pull physics out of that because there are a lot of things disentangled. So it's useful to think about when you don't have those same spectroscopic classifications, it's useful on one hand, but on the other, how are you going to separate if there are actually multiple populations? And that's where I'll end. Thanks.
Okay, thank you for the very nice talk. Maybe if there's one question, I'll go to Kyo.
So you said, one way to really control your selection effects is go for like a volume limited sample where you detect every FRB in that volume and you characterize every galaxy in that volume.
Yeah.
But does it have to be volume limit? Can it be like sample selected? Like, can I just say, let's only consider the ones that are coming from DESI galaxies, for example, because those are free. It's free-ish. Right? Is that a good way to think about it? Or do I really need to define a volume where I find every, with some criteria, I'm going to find every host?
Yeah, I mean, I think what we found in the supernova, you can do things with both. We found in the supernova case is that it really, the volume versus magnitude limited is important, mostly because supernovas span a huge range in luminosity. And so if you're just using your magnitude limited one, your rates and other things, like you end up biased in your explosion properties themselves towards the bright events. And there are other types of events that actually are more prevalent, but are fainter, and you just don't detect those. And I think we needed the volume limited samples to even understand our luminosity functions, to even then try to correct for that after the fact. And so it really comes from the fact, I don't know with FRBs, whether or not you have the same just difference in how intrinsically bright or not they can be, but I mean, a lot. And so that's an important thing to then understand. And especially whether the relative rates, are you missing huge fractions of them that would totally shift your rates if you don't have the volume limited sample.
Thank you so much. Lovely talk.
Great. Thanks again. Yeah, there's a question online that I will post on Slack. Oh, it's on Slack already. Okay, so we're going to hear from Anya Nugent on short gamma ray burst follow-up.
Okay. Okay, cool. Hello, everybody. My name is Anya Nugent. I'm a graduate student at Northwestern working under Professor Wenfei Fong, and my research primarily focuses on the host galaxies of short gamma ray bursts. So we'll use that knowledge that I've gained over the past few years to derive some lessons learned for the FRB community. So I want to start off by saying that short GRBs and FRBs are pretty similar. So both of these are very fast transients that emit their bursty emission in a single part of the electromagnetic spectrum. However, unlike FRBs, short GRBs have been consistently followed up for nearly the past 2 decades and have been shown to exhibit emission in other parts of the electromagnetic spectrum, specifically their afterglow emission, which appears in the X-ray, radio, and optical wavelengths. So short GRBs are primarily localized from the Neil Gehrels Swift Observatory, which detects about 8 short GRBs per year. Now, Swift is amazing because after it detects that initial gamma ray burst, it immediately follows up with its X-ray telescope to try to localize the X-ray afterglow of the burst. And typically, we can get that to about a several arcsecond position, which in most cases is good enough for us to make a host association, and also follow up with our optical and radio telescope to try to better localize that afterglow and see if it's appearing in other wavelengths. So after 18 years of community follow-up of Swift short GRBs, which has included associating as many short GRBs as possible to their host galaxies and modeling the stellar population properties of those hosts so we can better understand their environments, as well as understanding the GRB energetics, which are intrinsically connected to their redshifts, which we get always from the host galaxies. And with the joint detection of gravitational wave event 170817, the first binary neutron star merger to be detected by LIGO, along with short GRB 170817, we now know that short GRBs are derived from neutron star mergers. So with all of that information and this years of science we have on short GRBs, we can derive some lessons learned to benefit the FRB community in their quest to determine FRB hosts and the FRB progenitor. So I want to start off by showing you what our current sample of short GRB hosts look like. So between 2005 to 2021, Swift was able to detect 149 short GRBs. Now, Wenfei and I recently took this huge observational pursuit to try to associate as many of these short GRBs as possible to their host galaxies. And we were able to find very confident host associations for 84 out of this 149, which range redshifts from about 0.1 to 3.0. Now, for the population that we weren't able to find any host galaxies for, it's because those short GRBs occurred along high extinction sightlines, and so there's too much dust from the Milky Way that we can't see behind and determine if there's a host galaxy there, or the localization of the short GRB was so large that it encompassed multiple galaxies, and we can't know which one is the true host. Now, I will also mention that there's about 6 short GRBs that have really good localizations, even very good optical afterglow localizations that we have not been able to find a host galaxy for, even with deep HST imaging. So we think that those are maybe good JWST targets, and they could just be very high redshift candidates. Interesting to follow up later. So how do we make our host associations? So after Swift detects a burst, we wait for it to tell us that the X-ray afterglow has been localized, and we get all of those notifications through the General Coordinate Network or GCN stream, which are public notifications that we all subscribe to. And so that'll get us our several arcsecond position from which we can start to see, is there a host galaxy? The next thing that we do is we check public surveys. So my group's favorite surveys include the Legacy Survey, the Sloan Digital Sky Survey, or SDSS, and Pan-STARRS PS1. Now, these surveys overall are really great. They can get pretty deep. They can reach optical magnitudes of about 22 to 23 magnitudes. So that encompasses a lot of galaxies over a wide redshift range. I also want to mention that although it's not up yet, LSST will be up soon, and that will be able to reach even deeper optical magnitudes of about 26 mag, so very far into the universe. Furthermore, SDSS includes photometric redshifts for many of its cataloged sources and also has some spectroscopic redshifts and even some spectra that are available to download. And finally, the Legacy survey has this really cool tool called Sky Viewer, where you can view composite images of the Legacy, DES, SDSS, Galax, WISE, and VLAS surveys, and view some of their data products as well. So this is just a cutout from a position around a short GRB, and we can see the galaxies are highlighted there are ones where SDSS has a spectrum of those. So that's great if you need that information. And then the other circled sources are just sources that are popping up in the SDSS catalog that have photometry and likely also have photometric redshifts, which is great. So a lot of information available just on public surveys. So our method to confidently associate our short GRBs to a host galaxy is the probability of chance coincidence, which is essentially a function of how faint the galaxy is and the angular offset of the GRB to the galaxy's center. So if a galaxy is fainter or a GRB is further away in angular space from a galaxy, probability of chance coincidence goes up, meaning that there's less likelihood that those two events are associated. Sometimes what we end up finding is that our short GRB is right on top of a host galaxy and it's a very obvious host. In other cases, based on how faint the galaxies in a field might be or the localization of the short GRB, it might be a little bit harder and we have to do a little bit more digging to better understand what the true host of the event is. But I want to warn that you shouldn't exclude even poorer host associations. So one of the things that we did in our study of host galaxies of short GRBs was look at the confidence of our host associations in comparison to the stellar population properties we derived. So what we ended up finding was, luckily, a majority of our host associations were very confident. We're very sure that that's a host, and those comprise our gold sample. What we ended up finding for the hosts that we are less confident about is that those host galaxies tend to be fainter and occur at higher redshifts. So as redshift evolution is really important in understanding a progenitor, that's not a population we would want to exclude, even though their host associations are a little bit worse than our gold sample. So when do we use our telescope programs? Well, the most obvious case would be when we have a potentially very faint galaxy that we're not picking up. So this would be if you're checking your public surveys and there's absolutely nothing near the transient, but when you go in with a larger telescope or even HST imaging, you might see something there. So in the histogram on the right, what I'm showing is optical magnitudes of short GRB host galaxies in the green compared to the current FRB host galaxy population in the blue. And that's from Alexa Gordon's recent sample. So you should talk to her more about that. And what I want to point out here is that a majority of our short GRB host galaxies are fainter than the limit of most public surveys. So if we were only looking at public surveys to determine our host, we'd be missing a large part of our population, which wouldn't be good and wouldn't help us in understanding the environments that these can occur in. Furthermore, there is a growing population of FRB hosts that are fainter than the limit of most public surveys. And now as FRB detectors get better and they're able to see out to further redshifts, that population of greater than 22 mag hosts is going to increase by a lot. So it'll be important in those cases to use larger telescopes and telescope programs to be able to detect those faint hosts. So the next case to use telescope programs is to obtain spectra and photometric coverage for stellar population modeling so you can better understand the environments that your transients are occurring in. So typical recommendations would be to get optical and near infrared coverage, as well as a spectrum that covers the main spectral features of your host galaxy. So I also wanted to point out that our short GRB host program used about 36 full nights of telescope time in total to build all of the huge catalog that we needed to get all of the data to run our stellar population modeling fits beyond the data that we got directly from public surveys. So a lot of telescope time is needed to get a complete understanding of your host galaxies. So that brings me to my next point, which is on uniform stellar population modeling and how important that is in understanding host galaxies. So what do we mean by uniform? What you want to do is to attempt to have the same amount of observational data that you're comparing apples to apples. The next thing is, and probably the more important point, is to make sure that you have the same method for determining stellar population properties. So those would include things like your age, mass, star formation rate, metallicity, and the dust extinction. So in this plot over here, I'm showing star formation rates and ages derived in our most recent work on short GRB host galaxies compared to previous values that we found in the literature for a handful of short GRB hosts. Now, the ones that we found in the literature used different methods than we did to derive those properties. And what we can see is that when we're using different methods, we get slightly differing results, which can be really difficult when we're trying to find patterns within our host galaxy properties to see if our transient is preferring a specific kind of environment. Okay, so what can we learn with stellar population modeling? One of the most important things is to see how transient hosts trace well-known galaxy relations. So one of the most important galaxy relations is probably the star-forming main sequence, which I'm showing on the plot on the right. And we can see how dependent our transients are on the amount of star formation and stellar mass in the universe. So using mine and Alexa's short GRB and FRB samples, we can see what it looks like right now is that both short GRBs and FRBs seem to be good tracers of stellar mass given the star formation of their galaxies. They don't seem to be overly dependent on the amount of star formation or stellar mass. The next thing that we can do is we can use the ages and star formation histories we've derived from our stellar population fits to determine a delay time distribution and better understand progenitor formation timescales. And that's in fact what we did for our population of short GRB hosts in this study led by Mike Zevin. Was using our star formation histories, we were able to get a pretty good constraint on what our short GRB progenitor formation timescale distribution and therefore neutron star merger delay time distribution was. So the last point I want to make, and my cautionary tale, is to not forget about the strangest of hosts. So within our catalog of known host galaxies of short GRBs, we have this population of very faint host galaxies with absolutely no redshift constraints that have been solely detected with HST. Now, based on what we expect the luminosities of these galaxies to be at various redshifts, we're assuming that these are either low luminosity, low redshift dwarf galaxies, or very high redshift around redshift 3 star-forming galaxies. In either case, that's a pretty extreme environment that can give us a good constraint on the range of progenitor timescales and channels and environments that neutron star mergers can occur in. So don't discount the strangest of cases. If you're not seeing a host immediately, there could be something really interesting there to learn about your progenitor. So I want to finalize by saying, especially in the era of detecting many FRBs per week, make sure you're taking advantage of public surveys to optimize the number of possible host associations you have. Deep imaging when you're not seeing a host immediately and making sure that you're following up on those strange cases. And then finally, any host analysis you should do should be done in a uniform manner so that all of your stellar population properties are comparable. Thank you.
Thank you very much. Do you have any questions? Yeah. Yeah, Mohit, if you want to speak up.
Sure. Nice talk. Yeah. So I have this question. How do you treat host-less supernovae? Because now we have the increasing population of similar sources or FRBs as well. Now, so I know that traditionally you associate SGRB, as you discussed, with brighter hosts or hosts with smaller offsets. So if that's true, then do you correct for the local sphere effect? Means do you adjust your confidence limits now because you have analyzed the whole 146 Swift sample?
So we have not gone any deeper into exploring other methods for associating our hosts outside of using probability of chance coincidence, but I do know that the FRB community uses a path method, which I think is a little bit less biased in some aspects. I'm not an expert in path, but I think it looks at the location of the FRB within the host to see how associated it could be. So certainly there are other methods and other things you could explore. One thing that would be important is that if you're expecting your progenitor has an offset from the host galaxy, is maybe keeping that in mind. You might not always expect that your transient is right on top of a host galaxy in that case.
Thank you.
Thanks for the great talk. I have a question about strangest host that you
Yeah.
showed in the last slide, I think. So can you use like galaxy morphology from the imaging as additional information to constrain this?
Certainly. We're kind of starting to explore this sample. And so using any observational evidence that we have to see what these hosts could be. But yeah, it's certainly there's more ways we could explore this population.
Awesome. Thank you very much again. And now we'll have John Ruan and gravitational waves.
How do I go to the next slide? Wait, how do I go to the next slide? Okay. I'll start. Hi. Oh, am I good? Cool. All right. Hi. I was tasked with talking about gravitational wave follow-up and what FRB observers might learn from gravitational waves. You might be wondering why I put an image of a galaxy merger here, and that's because I'm not only talking about stellar mass black hole mergers, compact object mergers, but also lower frequency mergers that will be detecting lower frequency gravitational waves with like LISA. Okay, so I'll speed through my background because I think everybody knows this. Gravitational wave emission are emitted and detected by compact object mergers. Sort of generically, how you would do this is you detect the gravitational wave waveform. You compare it to a set of templates waveforms that are generated from numerical relativity simulations, and whichever one matches best, you assume that's true. And from that assumption, you could generate a sky map, a localization, and you can get very rough estimates on the parameters. So this is sort of the sky map that you get. So that's the two-dimensional sky localization. You also do get luminosity distance information as well from modeling the gravitational wave waveform. So you get a posterior on your distance, which means that you get this three-dimensional error volume, right? And then you can more carefully do inference, which means that you move around in parameter space, and so you have to rerun your numerical relativity simulations, which is more computationally expensive. But you can do this more carefully later on, well after the immediate follow-up has already and so what I'm showing here is, for example, posteriors on the masses of the two objects from a particular merger in LIGO. And then you can turn your telescopes to the to the localization region and see if you can see anything, right? So I'm showing you here the detection of the kilonova associated with GW170817 that Maria made. So that's just sort of a generic picture. Gravitational waves can come in a wide range of frequencies. So at the very high frequency, so this plot is showing you strain versus frequency at very high frequencies on the right. These are very high frequency gravitational waves detected by LIGO, but at slightly lower frequencies, you can get lower frequency gravitational waves that would be detected by LISA, that will be launched in 2030s, mid 2030s or so, and even lower frequencies, you get things like gravitational waves detected by pulsar timing arrays. I won't have time to talk about that. So I would just talk about LIGO and LISA follow-up. So in LIGO, again, we're talking about stellar mass black hole, stellar mass compact objects like stellar mass black holes and neutron star mergers, either black hole, neutron star, black hole, whatever combination. The sky localizations for LIGO are pretty large. For example, they're at least tens to hundreds of square degrees for GW170817. It was, we were lucky that it was unusually small at something like 30 square degrees. In that localization region, if you follow it up with telescopes, what you're basically looking for is a transient that's associated with a neutron star merger or a neutron star black hole merger, because black hole mergers you don't expect them to produce anything. So in other words, what you're looking for is some optical IR kilonova, or for some emission associated with a short gamma ray burst, like the prompt emission or the longer lived afterglow emission. And of course, both, the combination of the kilonova and the GRB would emit across the electromagnetic spectrum, so you would be doing this with a wide range of telescopes. Okay, so my bias is towards optical follow-up, so I will describe that in more detail. So what you would do is you would go to the localization region, and if you have a wide field camera imager, you would just start imaging, tiling the localization region. That's true if the localization region is large, or if the distance is large, and that's the distances from the luminosity distance from the gravitational waves. And that's because at very large distances, your galaxy catalogs are very incomplete. So you can't start targeting galaxies in a catalog, because your galaxy catalogs become like more than 50% incomplete once you go past like 200 megaparsecs or so. So you have to just blindly tile and hope you see something. Right. The alternative is if your localization region is pretty small, or if and the merger is pretty close by, which means that the galaxy catalog is pretty complete, you can actually go after and target individual galaxies. And so you just take your galaxy catalog, pick out all the galaxies that are in the localization region, and you produce a ranked list of galaxies. So how you would prioritize the galaxies is you prioritize them based on luminosity, redshift, and sky position, for example, if they're near the center of the localization region. Okay, so if you do this, you'll find that there are many transients in your localization region, right? So you've gone after this localization region, you've either tiled it or looked at imaged individual galaxies to look for transients, and you have found many transients. So this is just an example of a follow-up of a gravitational wave event where in the localization region, there's all kinds of supernovae and all kinds of other transients. Now, how you would pick out the sort of correct one is you would look for whichever one has a light curve that's similar to what you would expect from a kilonova. So that's what we're talking about, light curve shape, the general luminosity, and that really, and you can do that because we have a pretty good theoretical knowledge of what kilonovae from binary neutron star mergers look like. If we didn't have that, it would be much more difficult. Okay, so some takeaways I would say for folks who don't do gravitational wave follow-up, some things that I think you should know is keep in mind is that galaxy catalogs become 50% incomplete beyond 200 megaparsecs. So when you're looking at things that are far away, you can't rely on a catalog. So you have to get dedicated imaging, like new observations, dedicated observations, and whenever you propose for observations, follow-up observations, there will just know that there will be competing programs for very similar observations. Although that doesn't mean that only one of them gets accepted by attack, right? Because oftentimes even though they're very similar observations, they will have slightly different science goals in the eyes of the attack. It will be acceptable. So I'm a big supporter of collaborative follow-up programs. That's where instead of competing with each other, you should write proposals together. It minimizes duplicating efforts, right? So you don't basically try to get the same observations at the same time. And it also minimizes unnecessary competition on attack. And lastly, infrastructure, for example, GCNs are really important, and we've already seen some discussion on VO events. All right, so very quickly, I have time? Okay, good. I'm going to talk about LISA follow-up. So this is lower frequency gravitation waves. These are mergers of not of stellar mass black holes, or compact objects, but of intermediate mass black holes, right? So 10 to the 3, 10 to the 6 solar mass mergers. So these are in the centers of galaxies, and the galaxies are merging. So what I'm showing you here is a simulated galaxy where you see the X's mark the black holes, and the central black holes are merging as well. So for in LISA, so LISA is not launched yet, so these are all sort of projections. But in LISA, the sky localizations are going to be much better than they are for LIGO. So the LISA sky localization, it actually decreases over time, so it's temporarily evolving. That's because LISA makes a first detection of a merger of these two massive black holes. It can be days to weeks before the actual merger, and then it's very low signal to noise at first, but then it will follow it over days and weeks until the actual merger, which means that you build up your signal to noise over time, and so the localization region shrinks over time. So this plot is showing you the localization region, the area, as a function of time from a month before the merger to just before the merger, and you can see the localization region decreases to something like 1/10 of an arc minute or so. So which is better? All right, so how you would do this, how you would do a follow-up in LISA is then, again, you would take your wide field imager, you would image the localization region, and this is showing what this image is showing is from a simulation of galaxies, of galaxy formation, picking out all the galaxies that's in the simulated LISA localization region. And what you would be looking for in your telescope observations is sort of electromagnetic signatures. So for example, for a massive black hole binary, a lot of people, if it's in a gas-rich environment, a lot of people have said, you would get a circumbinary accretion disk around the binary. And due to torques on the disk around the binary, the disk emission would be periodic. So above that's showing you like a hydro simulation of the circumbinary accretion disk. Below is showing you a light curve of the emission from that disk. And the panel, the top panel is, you can see that sort of sawtooth pattern. That's the periodicity in the light curve. Below is essentially the periodogram. You can see there's peaks in the periodogram that correspond to periodicities in the light curve. And you would try to look for something like this. There's a lot of other signatures. This is just one of them, and it's easy to understand. So that's why I showed you this. However, it's entirely possible that the environment around the binary is not gas rich, and there is no circumbinary accretion disk. In which case, there really is no electromagnetic signature, so you're just left with a whole bunch of galaxies in the localization region. What do? Well, first you can make a redshift cut, right, just based on the luminosity distance from the gravitational waves. You can try to do other things as well. So for example, you can make a cut on galaxy mass based on scaling relations. So I'm showing you here is the scaling relation between black hole mass on the y-axis and stellar mass of the host galaxy on the x-axis, and you can see that black hole mass increases with stellar mass, which makes sense. And because black hole mass is given to you from the gravitational wave waveform, you can sort of make a cut on the stellar mass of the galaxies in the localization region. If you try to do this, though, it turns out that people have projected what you would see when you try to do this. What you would see is that you are left with a lot of candidate galaxies. So people have estimated that you would be left with something like 10 to the 3 candidate host galaxies are expected after both this redshift cut and the host galaxy mass, and that's because the scaling relations have a lot of scatter. What the plot is showing you is just basically what the number of candidate galaxies are expected in the 90% localization region. In the red is showing you it's at the time of merger. And the x-axis is showing redshift, which is not important, but at a fiducial redshift at say 1, what this plot is showing you is at merger, there would be something like 10 to the 3 candidate galaxies in the localization region, which is a lot. Okay, so we will be sort of screwed. So you're just in the localization region, if you take images, you would just see a whole bunch of galaxies. Which one is the actual host galaxy? It's not clear how to do this yet. I think we'll need to essentially combine a whole lot of different approaches. So some sort of takeaways from Lisa follow-up. I think a firm sort of theoretical understanding of what for example, like the host galaxies actually look like will be really important. To actually identify the exact host galaxy, you'll really need a combination of different approaches, and not just any one particular cut a selection cut in particular. All right, and especially for LISA, because these mergers, LISA will detect these mergers at such high redshift, you will need dedicated follow-up, right? So just looking at archival images from Sloan or something like that will not be helpful for LISA. That's it. Cool. Thank you.
Cool. Thanks again. Do we have any questions for John? I guess maybe at what point do you throw away the high redshift things?
Oh, for example, for LISA follow-up?
Yeah.
Yes. So yeah, LISA is mostly sensitive to mergers of, black holes that are like 10 to the 5 solar masses, and it can detect them out to like redshift 10, right? So basically, these are dwarf galaxies at high redshift, and beyond redshift 2, there's no way like you're going to really detect them. So at what point do you start ignoring the really high redshift stuff? Like very quickly. Yeah, most of the LISA mergers that you will not actually see the host galaxies for.
Cool. Daniele?
Yeah, I'm sorry, I don't know much about LISA, so maybe this is stupid, but can't you use like the relative direction of the telescopes as they vary in time compared to the black hole to constrain the position? Shouldn't you see like variations in the signal to noise as the telescopes move?
Variations in the signal to noise, the telescopes, the 3D LISA detectors are always moving.
Yeah.
And so you're saying, should you see
like I expect that the signal to noise will be higher when the telescopes are perpendicular. The plane of the telescope is perpendicular to the signal from the merging black hole.
Okay, and you're saying, so as the 3 detectors move, the signal to noise will change as So what I'm showing you there doesn't take into account the motion of the spacecraft. So those details, because LISA is 10 plus years away, those details were not taken into account in those projections. All that's saying is just basically, if you assume some constant sensitivity, how large the localization region will be.
Okay.
Yeah. So those sort of details are not taken into account here.
Okay. Are there any questions for any of the speakers from the session? Okay. If not, we'll thank John and the speakers again.